Okay, welcome to the lecture here. We're going to continue on with chapter 2, and then we're going to go into hopefully chapter 3 as well. Again, the notes can be found up there online on our Canvas site. And again, make sure you do put here in the chat box. Thank you. Okay, so we've been talking about chapter 2. We're talking about really kind of conversions, conversion factors, equalities, and sort of doing dimensional analysis. So a couple of reminders on those things. Again, when we have an equality again is really two values that are on different scales, but they basically mean the same thing or represent the same amount. So like 100 pennies is the same as $1. They both represent the same amount of money. And from any equality that you come up with, you really can write two conversion factors, which are really just fractions, where you put one of the sort of values up on top, the other one on the bottom, and then you could flip it. And we use those conversion factors when we do these type of problems in chemistry. We really try to perform what's referred to as dimensional analysis. And dimensional analysis is a way to solve problems where we basically show all the units and basically the units canceling each other. So we could clearly see what gets canceled, what doesn't get canceled. And basically we go opposites in terms of those units. So for example, if we had pennies up on top, we started with, we would want to get rid of pennies. So pennies would go on the bottom and say dollars would go up on top. And again, that is sort of the process that we use. And when you solve problems in chemistry, you always want to make sure you show all the units, kind of like what we did, setting up, canceling out. And basically when we math-wise, what we're doing is multiplying across the top and coming back and dividing by whatever's on the bottom. In terms of significant figures, as we talked about, for the most part, anything kind of in the middle is usually a conversion factor or an equality. And you don't necessarily have to look at those significant figures. Although, again, your book and so forth, as we talked about last time, if it is sort of a metric to English conversion, you really should look at the significant figures involved in that conversion factor. If it's metric to metric or English to English, you don't have to. I did say for us in here in lecture, you could consider any sort of conversion factor that's a true conversion factor, not one just given to you in the problem or something like that. You could kind of consider it as, sort of an exact number. Probably 9 times out of 10, if you kind of go with the original number, that's usually around what the correct significant figures should end up being. And especially if you're using kind of metric to metric and English and English sort of conversion factors. So if we look at, say, something like what we got here, we want to know how many minutes there are in 1.6 days. So when we go approach this and when you do conversions, there are many different sort of routes that you might be able to take on the same type of problem, just depending on sort of which path you choose. So clearly we want to end up with, we're starting at days, and we want to end up with minutes. So we need some of those conversion factors. So we know perhaps one day is hopefully only 24 hours. Again, that's an equality. From that equality, we could write two conversion factors. We could write one day up on top over 24 hours, or 24 hours over one day. We also know that in 1 hour, there are 60 minutes. Same thing here, that's an equality. So again, we could write two conversion factors, 1 hour over 60 minutes, or 60 minutes over 1 hour. Again, we're not going to use all these conversion factors in a problem. You're just going to choose sort of the one that you need that's going to help you. And again, from any equality, you basically can do that. So we're going to start with the 1.6 days. And again, we want to work this problem with dimensional analysis, which is going to show our units basically canceling. So the idea here is, again, as we sort of touched upon last time, Although, it's not really written as a fraction. That very first original number, if you want to think about it, is sort of over 1. And really what that means is we can see that the days in terms of units are up on top. So when we come to our first conversion factor, we would want to use the guy on the right here, because opposite of that is where we want to get rid of the days. So 1 day on the bottom, 24 hours up on top. And the idea behind that is we're multiplying everything on top, we're dividing everything on the bottom. So essentially, if we just look at the units, we're essentially taking days divided by days, which means it will equal 1. Again, same idea. If you took 2 divided by 2, that also would equal 1. So units work the same way. They essentially will cancel each other out. You could, at this point, if you wanted to, get an answer, or you could continue on with the calculation. So I'm going to continue on with the calculation. If you get an answer at this point, you probably want to avoid a lot of rounding until the very end. So if I did continue on and I look at the units, I now have hours up on top. So to get rid of it, I need to go opposite of that and take hours, which are on the bottom. So I want to use the conversion factor over there. And that's going to be 60 minutes up on top, 1 hour on the bottom. Again, hours are going to cancel each other out. The last unit standing, as we can see there, is minutes, which is good because that is what we are looking for. So again, math-wise, what we're doing is we're going to multiply those two numbers. We're then going to multiply this number as well. Multiply as many numbers as you want up on top, then hit equals. And then we're going to come back basically and divide by what we got on the bottom. In this case, it all happens to be 1. If you had multiple numbers on the bottom that were different than 1, you would want to, as I talked about, I think last time, hit the divide button, hit and divide it by the first number, then hit equals, divided by the second number, hit equals, and divided by the last number and hit equals. In this case, obviously, they are all 1s, so you don't really have to do the division part. So essentially, we're going to take 1.6 times it by 24, times it by 60. That is going to get us an answer on our calculator of 2304 units are going to be minutes here. First off, any questions on the calculation? Looks like what we got going there. Make sure I punched it in right here. 1.6 times 24 times 60. Now let's talk about significant figures. So this is really an exact number here. This definition, this guy is also an exact number. They're on the same scale. That means if we default back to our original number, like probably 9 times out of 10 in most cases, this number has 2 significant figures, which means we should go to here. Again, we don't want to do any extreme rounding, so we should end up with 2,300 minutes written like this, which is 2 significant figures, are 2.3 times 10 to the 123 minutes, which is also 2 significant figures. Any questions on that calculation there? Yeah, so good question. So on quizzes or exams, in terms of sort of what you need to show, if it helps you to grab a different color, we'll go with green. If it helps you to write all this stuff out, you can. Not really necessary. So what's necessary besides all the extra drawings here is sort of this part here, where you show the units canceling, the setup and the dimensional analysis. So that part of it, that's sort of in the green box, is really what you need to show. If it though helps you to do all the others, you're absolutely not a problem. You could do that, but you don't have to show it for credit. So when we say kind of show work, this part right here is really the work that you need to show. Other questions on that? So whenever you do any calculation here in chemistry, you should always try to give the answer to the right number of significant figures. So you should always give it to the right number of significant figures. Definitely in these early chapters as well, all the time, but extremely much in these early chapters, since it's all about sort of significant figures. So you should always give it to the right number of sig figs there. Yes, you definitely can use your calculators on tests and quizzes. Otherwise, I would think you would probably run out of fingers pretty quickly and stuff like that. So, yeah, you definitely should use a calculator. It should hopefully be the one you're using during lecture, so you know how to use it. But yeah, you definitely will need a calculator. I wouldn't be able to do it, with my hands or anything like that. So yeah. Any other questions on that? All right, so let's take a look at another sort of conversion type problem here. And here's sort of what we got to in terms of our answers. Let's take a look at this one. Here we are, we're walking at 65 meters per minute, and we want to know how many minutes will it take us basically to walk a distance of 7.5 kilometers. So in this particular problem, we're given several pieces of information. One piece of information is basically the distance we're going, right? So we're going basically 7.5 kilometers. We're also sort of given our rate, if you will, which is 65 meters per minute. The rate is really how far you go, what distance you go in a particular amount of time, like when you drive 65 miles per hour or something of that nature. So really, this rate is what's going to convert our distance into time, because we ultimately want to know time, right? We want to know how many minutes is it going to take. So when we look at these two values, we have a situation here where we have unit problems. And what we mean by that is this sort of length or distance is in kilometers, while this guy here is in meters. So if you try to use both of these guys together, it's not going to work for you because they're in different units and you will be off. So you have to do a conversion of one of them. So you have to either make the kilometers into meters, and then you could use the meters per minute, or you can convert the meters per minute into kilometers per minute. The easier move would probably be to take the kilometers to meters first. And then once you have it in meters, you could use that rate again as a conversion factor, meters on the bottom, minutes up on top. So that's sort of the game plan that we want to do here. That means ultimately we want to figure out that conversion or equality that we need between kilometers and meters. And in 1 kilometer, there is 1,000 meters. That means, again, we could do our two conversion factors, 1 kilometer over 1,000 meters, or 1,000 meters over 1 kilometer. So that's what we're going to start with first. We're going to start with just the distance part to get it into sort of the right units. Again, although not written as a fraction, the kilometers are up on top, which means to get rid of it, we need to go opposite. So we have to use the conversion factor on the right. And that would give us 1 kilometer is 1,000 meters. Again, kilometers divided by kilometers are going to cancel. We're going to basically multiply what we got going up there on top. And that would get us 7.5 times 1,000, 7,500 meters. So when we're saying we're going to walk 7.5 kilometers, we're basically walking 7,500 meters. The good news about that is we have now converted it into the same unit as in our rate that was given to us. So the rate's going to allow us to go from length or distance to time, and we're going to use it as a conversion factor. So even though it's given to us in our problem, we could basically use it two ways, 65 meters per minute, or you could flip it around and use it with the minutes up on top and the 65 meters on the bottom. So again, even though it's specific to this problem, it can be used really as a conversion factor here. Any questions on that there? So we're going to use that conversion factor to do the actual conversion. So we will take our 7,500 meters Again, using dimensional analysis and opposites, so meters again on top, which means to get rid of it, we need to use the meters on the bottom, which would be that version. So we'll put 1 minute up on top and 65 meters up on the bottom. In terms of units, meters and meters will cancel as we're dividing them. What we're essentially doing here is we're multiplying. So we're essentially taking 7,500 times 1 in that case. You hit equals. And then we're going to come back and divide by what's on the bottom there. So we're going to divide by 65 and hit equals. And on your calculator, you probably get this number spit out to you. Why not? I'll write them all. And the units here would be meters, minutes in this case, which is what we're looking for. Now, when we're trying to think about sort of our significant figures, we want to think about, really what we're using here. So if we kind of go back, we have this guy here, which was 2 significant figures. This is an exact number, which means this guy should have 2 significant figures, which when we carry down to do our last calculation, 2 significant figures divided by this. This again, technically is not a true conversion factor that you technically find on a table. It's specific for this particular problem. And that 65 actually has 2 significant figures, which means we should actually go to 2 significant figures, which would put us right there at that second one. And that means that we should end up with 120 minutes. Or again, if you want to do scientific notation, 1.2 times 10 to the 2 minutes. Any questions on where the numbers came from? Why we did any of those things? And again, you should always try to give it to the right number of significant figures. And, you could almost, in 9 times out of 10, like I said, look at that original number, and you'll probably either be correct in terms of the significant figures, or you'll be fairly close to the right number of significant figures. So again, you can come across some conversion factors like what we see here, where you should take them into account. But 9 times out of 10, if you kind of look at that original number, it probably will give you, again, I won't say 100% of the time, but pretty close, the right number of significant figures your answer should have. Any questions on that? Again, you could do it all in one step. You could do it in individual steps like I did here and get an answer and continue on with the calculation. But you do want to make sure if you are getting answers at individual steps that you don't do a lot of rounding until the very end and kind of clean it up at that point. All right. So let's give you a couple to do here. They agree with us, so that's good. So why don't you give this one a go, see what you come up with. Give you some equalities that would be helpful here. So why don't you take a minute or so and see what you come up with. You could put the answer in the chat box to see where everybody is. You go to your local AM/PM, you get your 32 fluid ounce drink of Diet Coke from the Thirst Oasis. How many gallons of Diet Coke did you drink? So take a couple minutes, see what you come up with. Okay, I'm starting to see some answers roll in. So let's see how we all did here. It's looking pretty good in there, I think. All right, so again, we have these 2 equalities. And we could write, again, 2 conversion factors for each. We could say 1 quart is 32 fluid ounces, or 32 fluid ounces is 1 quart. We could also go 4 quarts is 1 gallon, and our 1 gallon on top is 4 quarts. Again, we're going to start with 32 fluid ounces, which was given to us. So that's where we're going to start our conversion. 32 fluid ounces. Again, not written as a fraction. We're assuming that is on top. So we want to get rid of it by putting the fluid ounces on the bottom. In this case, we will use the one on the left. 1 quart up on top, 32 fluid ounces up on the bottom. Again, fluid ounces would cancel. If I were to stop the calculation right at this point, the units I would be in would be quarts, but that's not really what I want. I do want to get to gallons, so we need to use one of these conversion factors here to do that. Quart is up on top. Again, I could get an answer, or I could just continue on. And to do that, we will want to put the quarts on the bottom there. That's going to give us 1 gallon and 4 quarts. Again, quarts will cancel out. We're going to multiply across the top and hit equals. We're going to divide by the bottom, hit equals. And we're going to divide by the second number, hit equals. And when you do all that good stuff, I do believe what everybody was putting there in the box, you do get your 0.25 gallons. Again here, 2 sig figs should probably end us with 2 sig figs here. Now, this is the answer. The answer of 1/4 is not the answer. It just makes me think you're too lazy to divide it. So make sure you do divide it and get an actual number or decimal point, something like that. Don't leave an answer in a fraction. Not maybe for this, but I have seen people, leave answers like 325 hours, over 455 days or something like that. And they just kind of circle it. So don't ever sort of leave an answer in fractions. In chemistry, do kind of divide it out, get a number with a decimal points into the right sig figs. Any questions on that calculation there? Okay, so why don't you try the next one here? See what you come up with. There we go. Hopefully they agree with us. They should. Good. All right. During surgery, a patient receives 5 pints of plasma. How many milliliters was given? Here's again a couple of qualities that might be helpful for you. See what you come up with. Take a minute or two. Let's come up with it. Okay, so looks like we're filling up there. So let's take a look again. In this case, we're going to try to get from our pints to our milliliters. And we do have our equalities. Again, from both of these, we can write 2 conversion factors. We got our 1 quart over 2 pints, or our 2 pints over 1 quart, 1 quart over 946 milliliters, or 946 milliliters over 1 quart. So since we have pints, we're going to start with that. That's going to be 5 pints. Again, the units of pints are up on top. So to cancel them, we do want to have it on the bottom. So we're going to use that conversion factor there to do that. The pints will cancel at this point. If we stop right here, we are in units of quarts, which is close to what we want, but we do want to get it to milliliters by using one of these conversion factors. And obviously here, quarts are up on top. So to get rid of it, we want to put the quarts there on the bottom. That's going to be 946 milliliters is 1 quart. Again, quarts and quarts, which are divided by each other, would cancel. Math-wise, again, we're multiplying up there up on top. We're then going to come back, divide by the first number there, hit equals, divide by the second number, hit equals. And if we do all those things there, 5 times 946 divided by 2 gets you a number of 2365 here. Units would be milliliters in terms of what comes out on your calculator. In terms of sort of sig figs, you pretty much don't have to worry about this guy. Technically, probably should worry about that guy. That is 3 sig figs. But our original number here, like I kind of said before, is usually pretty close. So this guy has 2 sig figs, which means we really should end up at two significant figures. So again, this really should end up at 2,400 milliliters, or again, if you want to do scientific notation, 2.4 times 10 to the 3 milliliters. Either way is perfectly fine in this particular case. Looked like you guys did pretty good on that, so that's good. Any questions on that calculation? Okay. Let's then finish it out with one last conversion here. All right, so you're stranded 125 miles away from home there, and you need to walk at home because you know you're bored. And you're going to walk at an average of 55 feet per minute. How many days is it going to take you to get home? So a couple of equalities that might be helpful for you. So take a minute or two, see what you come up with here. Did when we were talking about sort of our distance and our rate. Again, we have this rate here. We really could use as a conversion factor. It could be used just the way it's written. We could also, if we needed to, put the minutes up on top and the 55 feet there on the bottom. But we do have a sort of a unit problem again. We have miles for one of them. We have feet for the other. So we do have that difference in units, which we need to do a conversion. So I'm going to take the miles to feet, so I could just use this the way it is. Again, you could have done the opposite and took the feet to miles, but they should come out the same. So the first thing I'm going to do is, again, going to use this here as a conversion factor to convert my miles into feet. So I have 125 miles. Again, miles are up on top. So I want to go opposite of that and go 1 mile on the bottom is 5,280 feet. Miles will cancel each other out, and we will end up with 125 times 5,280. Looks like 660,000 feet. Seems like a lot of feet. 660,000 feet we're going to walk. Again, this is good because this guy's now in feet. Our kind of rate here is in feet, so we can use it. So we'll pick up the calculation with that, 660,000 feet. Again, feet are up on top now, which means I do want to use the conversion factor like this, which will put feet in the opposite location. So that's going to give me 55 feet per minute. That's really what's going to get rid of the feet. And now we're in minutes, which is a unit of time, which is good because ultimately we're looking for days, which is a unit of time. At this point, again, if I stop the calculation, I would be in minutes. So I could then go minutes to hours, one path that you could do. So minutes would go on the bottom so that they cancel. So that's 60 minutes, 1 hour. If I stop right there, the minutes and the minutes will also cancel because they're opposite. And we would actually be in units of hours, which is close to days. So we have one more to go, which is our hours to days. Remember that there's only 24 hours in a day, not 60. And again, our 24 hours would go on the bottom. 1 day would go up on top. Again, hours would cancel. Last unit standing is days, which is good because that's what we're looking for. So again, math-wise, we are multiplying, and we are multiplying, and we're going to hit equals. And again, I would highly recommend dividing by the first number, hit equals, divide by that second number, hit equals, and divide by the third number and hit equals. So you don't try to put it all in at once on your calculator and end up with the wrong number, which is a very common mistake. Basically, we're taking 660,000, we're divided by 55, hit equals, divided by 60, hit equals, and divided by 24, hit equals, and you end up with this number here, 8.33333, whole bunch of threes, days, basically. First off, any questions on the setup here? So let's talk sort of sig figs, really where it should end up with in this particular problem. Um, and truth be told, there actually was a title. They probably will be provided for you on the test, the conversion. Again, some things may not like 60 minutes in an hour or 60 seconds in a minute, so some of those stuff you should hopefully know. But, maybe something like 5,280 feet equals 1 mile would be provided. Those type of things would be provided for you. Obviously, you just need to know how to use them correctly. In terms of sort of significant figures, this is really an exact number here, so we don't have to worry about it, right? This guy is an exact, so you don't have to worry about it. This original number had technically should actually have had 3 significant figures, even though I didn't really write it correctly there with 3 sig figs. But technically, if we're keeping track, it has 3 significant figures. And again, this conversion factor here is really not a true conversion factor, if you will. It's one specific for this problem, which means that 55 feet is probably a measured value and has 2 significant figures. So really based off of that number right there, you really should probably end up with 2 significant figures here at 8.3 days. And again, technically speaking, this probably should have been written 6.60 times 10 to the 1, 2, 3, 4, 5 feet, which would give us our 3 sig figs. Or, you can just kind of keep track of them and clean it up there at the end. Any questions on that there? Any questions on conversions, conversion factors, equalities, dimensional analysis? And again, what we're showing here in terms of what you need to show on an exam or a quiz is again really this part here. And probably for this one as well, the top part, right? Those just the calculation parts is technically what you would need to show. And by setting it up like I'm doing here, this is again what is referred to as dimensional analysis and sort of the way you're supposed to set up problems when you solve for them in chemistry. Any questions on any conversions or any of that type of stuff? Okay, so the next topic we're going to talk about is actually density. We'll ignore the 8.33 because it's actually supposed to be 55.0, but I didn't change it on the handout. So density here is 2.7, which is the section in the book, obviously. But the density of an object is basically will tell us whether or not sort of an object will sink or float depending on its density. So typically if something, for example, is more dense than water, it will sink. So if something is more dense, it will sink. And if something is less dense than, say, water, it will float. So for the most part, liquid water, is often thought of as having a density of 1 gram per milliliter or 1 gram per cubic centimeter. Density does change with temperature, just so you know. But, in sort of most chemistry classes, or if you're just asked in general, what is the density of water, liquid water? It is basically 1. Ice, which is also water, is actually less dense than liquid water, and that's a very unusual sort of property. Most things in their solid state is more dense than their liquid state. The reason why something like ice, for example, is less dense is when all those water molecules basically come together in the solid state. They really don't come together very tightly, if you will. They create a lot of open volume in the middle of them. And that open volume actually gives water a kind of unusual property. It gives the solid version of water being less dense than the liquid version. Usually when we think about things that are solid, we usually think about things being packed in fairly tight to each other. And again, with water, just because of the way it comes together, it actually does create a lot of this open space between the different water molecules and actually lowers the density. That's why when we put ice in our drink, right, it floats to the top, usually is where we find the ice. And that's really because our drink is mostly water, so it's able to float. Here's some examples. Cork there is floating up on top. It is the least dense. The heaviest guy there would be the guy that's furthest down there, would sink to the bottom. Aluminum sort of next. And we have ice, which is kind of floating, but less than that. So you could really separate out things, let's say in a graduated cylinder, and things that have different densities. You'll see these different layers sort of happening, where the least dense layer would be up on top, the most dense would be on the bottom. And kind of like the picture there, you literally could kind of throw something in there, and you could get it to kind of just kind of hang between a couple different layers. And what you would know is that this guy here that I just drew is less dense than the layer below it. It is more dense than the layer above it. And that's why I was kind of sitting there in the middle of the two. So how do we calculate density? Well, density is really the mass of the substance to the volume. And the formula is basically the density is mass divided by volume. In most cases, the mass is grams and the volume is in milliliters when we talk about units, or grams per cubic centimeter. Again, if you remember, 1 milliliter is the same as 1 cubic centimeter. So those are very common sort of units that we see with density. How do we get to, say, cubic centimeters? Again, that's usually something that's measured, like you take the length times the width times the height of an object. And again, if each of them are measured in centimeters, when you multiply those all together, you get cubic centimeters, which is a volume. So that's one common way that you could kind of get the volume of like an object that's maybe like a square or something like that, a cube. Milliliters, very simple way is, you could just actually take a volume reading, right? And when we take the volume reading, we always want to read from the bottom of the meniscus. And that's the curvature of the liquid that we commonly will see. And you literally can just take a volume reading. So those are two really common ways. Now you can think of density as obviously D is equal to M divided by V. If you want to solve for volume, that would be the mass divided by the density. And if you wanted to get mass, it would be the volume times the density. So that's sort of three very common ways that we rearrange this formula here. Some people like to remember the DMV triangle. Everybody loves the DMV. And that's like the DMV triangle there. Density is mass divided by volume. Mass is density times volume. And obviously volume is mass divided by density. So sometimes people remember this DMV triangle as a way to remember how to kind of correctly rearrange those guys. You will be asked, obviously, at some point to maybe solve for any of those three things, depending on the information given to you, the density, the mass, or the volume. Any questions on that there? Substances, again, that have higher densities usually contain particles that are fairly packed very tightly together. And that's why when we talk about sort of solid state, that's usually what we see happen sort of in the solid state, is everybody pretty close to each other. Lower densities, they typically are further apart. So when we get to the liquid state, things are a little bit more spread out. And again, the density starts to get a little bit lower. And metals such as gold, lead have very high densities because those atoms are packed in there very, very tight. And again, as you can see here, here's lead and aluminum. They have pretty high densities compared to something like water. As I mentioned before, these are the common units. We won't get too much into the gas, but when we talk about gases, they oftentimes are given in terms of density grams per liter. But overwhelmingly, the units that we will see for density will be these two in this class, either grams per milliliter or grams per cubic centimeter. And really, the value will be the same because of that one-to-one relationship between a milliliter and a cubic centimeter. Here's a chart of densities. Obviously, you don't have to remember it or anything like that. Again, water at 4 degrees Celsius, as I mentioned, does change with temperature. And again, most people will consider water 1. So kind of, all these guys would technically be less dense than water. Something like mercury obviously is more dense. And these guys over here as well have some higher densities. Then we see some of our metals with very high densities happening over here. So a lot of solids, again, obviously if you threw any of those guys sort of into water, it should sink. And if you threw any of these sort of guys into water, it should probably float as well. We'll skip that, I think. So two common ways to figure out the volume we just talked about. One, again, is very simply, you kind of take a look at it and take a volume reading off of a device. The other common way to get the volume, like I said, if it's something like a cube or something like that, you could take a ruler out and do those 3 types of measurements: length times width times height. The third very common way that you see a lot when you talk about density in order to figure out the volume is what is known as volume by displacement. So basically the idea of volume by displacement is if you have sort of a, say, graduated cylinder here of some water, and it has an initial volume with nothing in it. If you take like a solid and you basically dump it in there, what's going to happen to the volume of the liquid that's in there is it is going to end up rising when you put that solid in there. And we will end up with a final volume. Now, what happens is that solid that you put into the water will displace a volume that's equal to its own volume. And what that essentially means is if we take the difference from where the volume started to where the volume ended, that would give us the volume of the object, which is typically the final volume minus the initial volume in this particular case. So again, this is a very, very common way that we calculate the density of an object is by doing that. So for example, to get these measurements in the lab, as you can see here in the picture, you could use a balance and simply get the mass of the solid. And as we can see here from the reading, it is the mass is 68.6 grams. This is our graduated cylinder with some liquid in there before we started with, and we will take their reading there because I can't see the scale on that picture. But the initial volume before we put the solid in was 35.5 milliliters. The final volume after we carefully put the solid in there, as you can see, it's sitting right there, jumps up to, looks like 45 milliliters. So we could use our density, which is our mass divided by volume, like they did on the bottom. We could find the volume of the object here by taking the final minus the initial. So in this case, we would take 45.0 minus 35.5 milliliters. And as it says on the bottom there, that will get you 9.5 milliliters. So to calculate the density like they did on the bottom there, we would take the mass, we would divide it by our volume, and just like they have there, when you do that on your calculator, you are going to get this number that comes out 7.221052632. By the way, the units here do not cancel, so they both remain. The number stays with the grams and is per 1 milliliter. Now, we want to think about, in this case, sort of what we're doing in terms of significant figures. So the first thing that we did was we actually did some subtraction here. And remember that when we do subtraction, we're looking at the number of decimal places. And it's the smallest, which means if we look at our first number, it went to 1 decimal place. We look at our second number, it went to 1 decimal place. So when we gave the answer for the volume, it went to 1 decimal place. So that number is correct. Remember, though, that although it has 1 decimal place, like it says on the bottom there, this number has 2 significant figures. So that's important when we do our last calculation here. The top guy here, as it says, has 4 significant figures. Bottom guy has 2 significant figures. That is why we should take our answer, like they did, to 2 significant figures. This becomes 7.2 grams per milliliter. Any questions on that there? So that's a very common thing that occurs, excuse me, in density problems. You will oftentimes will do this volume by displacement. It will require you to do some subtraction, and sometimes people get lost with the significant figures where we should end up. So you want to kind of keep track of it along the way. Any questions on that particular one there? All right, so why don't you give this one a go, see what you come up with here. Okay, so let's take a look. I see some answers rolling in. So again, here we're looking for the density. So if we got something to write with, there we go. Density again would be our mass divided by volume. And we are given the mass of the object, which is 48 grams. We have the initial volume here of our graduated cylinder. And as you can see, when they throw the object in there, we get to our final volume that's here. So our initial volume is 25 milliliters. Final volume is 33.0 milliliters. So again, this is a volume by displacement, the very badly drawn straight-ish lines. The difference between those two volumes is the volume of our object in this particular case. So we want to first get that by subtracting. So we would take the volume of our object here is 33.0 minus 25.0 milliliters. That is going to get us 33.25 minus 25. And again, 33 minus 25 is 8. And it is supposed to be 8.0 milliliters here. Again, we're subtracting. So we go to decimal places, 1 decimal place there, 1 decimal place there, gives our volume 1 decimal place there. Also gives this guy a total of 2 significant figures when we carry on with our calculation. So our density here would be our mass divided by volume. And that's going to be 48.0 grams divided by 8.0 milliliters. Again, the units here are not going to cancel each other out. So we should end up with 6.0 grams per milliliter. Again, because the final calculation we did, we were dividing. So we do look at significant figures. So that's 3 significant figures. And this guy here should have 2 significant figures, given our answer 2 significant figures. Question on that one there. So again, you might do a lot of multiple sort of calculation steps. You want to make sure that, you don't necessarily have to round along the way, but definitely by the end, you want to make sure you're keeping track of everything in terms of significant figures, and make sure that you do kind of clean it up at the end. Okay. And they agree, so that's good. So if the volume and the density of the sample are known, the mass in grams can be calculated by using really density as a conversion factor. So, if we do have density as a conversion factor, we could have grams over milliliters, or you could use it with milliliters over grams. Again, you could use that density value as sort of a conversion. So why don't you take a second here? An unknown liquid has a density of 1.32 grams per milliliter. What is the volume of a 14.7 gram sample? So take a minute, see what you come up with. Take a look. So again, if you're not really sure where to start, sometimes people get into that problem where, they're maybe not sure kind of where to begin. You can very simply just kind of pull the information from the problem. So they gave us obviously a density that's 1.32 grams per milliliter. We also have a mass that was given to us, which is 14.7 grams. So if you just sort of check off things, you can see that the only thing you really don't have here for density is volume. So obviously that's a good place to start just in case, you maybe got a little confused. Remember when we rearrange that, the volume would equal mass divided by density. And we again could use this as a conversion factor. We could use it the way it is, 1.32 grams per milliliter. Or again, we could flip it around, put the milliliters up on top, and kind of approach it as a dimensional analysis type problem. We could start with our mass, which is 14.7 grams. Again, opposite of grams, we want grams on the bottom, which means we do want to use the guy on the right there. So a milliliter is 1.32 grams, and that will get us again on our calculator something like 11.1363636, so forth. Again, the grams will cancel here. We will be left with milliliters. In terms of significant figures, we're basically dividing. That's 3 sig figs. That guy there is 3 sig figs. That means this guy should probably end right about there. Looks like what I see in the box there. So 11.1 milliliters is our answer there. Any questions on that there? Okay. Let me try one more here. I think, come here. There we go. Hopefully that's what they got. Good. Oh, actually, we do have one more. John took 2 teaspoons of cough syrup for a cough. The syrup had a density of 1.20 grams per milliliter, and there is 5 milliliters in 1 teaspoon. What is the mass in grams of the cough syrup? Whew, that's a mouthful. So take a minute and see what you come up with here. Got some answers coming through there, looking good. All right, so in this particular information, we're definitely doing something with density since they gave us the density. That's 1.2 grams per milliliter. That also tells us that, we're going to be using perhaps a density formula. He took 2 teaspoons, and they also gave us a conversion or equality that there are 5 milliliters in 1 teaspoon. We want to know how many grams. So ultimately, we want to figure out the mass. They did give us the density. So one thing that we probably also need to figure out is the volume. So we have almost the volume what he gave, but it's in teaspoons. Obviously, the volume part of our densities in milliliters. So we do need to do that conversion to get everybody really into the right units. So we would start with that conversion, 2 teaspoons. Again, using that equality, we want to put the opposite unit on the bottom. So that's going to be 1 teaspoon. Up on top would be 5 milliliters. Again, teaspoons and teaspoons are going to cancel. And that's going to give us like 2 times 5, which is 10. And probably technically should have about 2 significant figures, 2 there, even 2 here if you look at this number as well. Now I have the volume, so that's now good. That means I could solve for the mass. So the mass is the volume times the density. So starting with my volume of 10 milliliters, using my density as a conversion factor, so I actually can use it exactly the way it's written because the milliliters there are on the bottom. That would give us 1.20 grams per milliliter. Again, the milliliters would cancel. We're going to multiply the guy up there on top, basically divide it by 1. So looks like we end up with 12 grams here of cough syrup. And sig fig wise, again, just following along, that has 2 sig figs. This guy has 3 sig figs. That means we should end up with 2 significant figures here for our answer. Any questions on that particular one there? Any questions on density, how to calculate it, mass? Obviously, you do need to be able to calculate any of those 3 things given the proper information, density, mass, or volume. Obviously, you need to know how to do volume by displacement and all those things. Any questions on any of that? Okay, so actually, we're going to wrap up chapter 2, I think, with that. We're going to skip specific gravity, so you don't have to worry about specific gravity for us. We're not going to talk about it, I think. So for that, that will end chapter 1. So you don't have to worry about specific gravity. Okay, so give me a second to get chapter 3. We'll get energy in this chapter. There are going to be some sections of the chapter which changed my mind. So there's some sections of the chapter that we really won't cover. So I'll try to let you know, obviously, when we get towards the end there. But there's some stuff about specific heat in this chapter. We're going to talk a little bit of it, but really not a lot. So definitely the specific heat part of this chapter. I think I spelled that badly. We're probably not going to cover. I think it's somewhere around section 3.4-ish or so, something like that. So let us get into this. So we're going to talk a lot about matter and energy in here a little bit. We're going to talk about sort of, again, some of the changes in matter that we see and what's going on when we do change those states. So we sort of touched upon it in chapter 1 when we talked about it, and we will talk about when the quiz is and all that kind of stuff in just a second before we're done today. So let's talk about matter. Matter really is, anything that does occupy space and takes up mass. So that's pretty much most things. Water, wood, plastic bags. As we talked about, and as we will again see in a little bit more detail in this chapter, matter really, can be sort of either solid, which, as we talked about, is usually when things are packed in fairly tight to each other. Liquid, where we still have things relatively tight to each other, a little bit more room for movement, as we talked about. Again, that's why liquids obviously are fluid, and gas, is that state where pretty much everybody has sort of broken apart from one another. That's what's causing the collisions that we associate sort of with gases, the pressure that we associate with gases. We could really classify matter also according to its composition. There are things that are known as pure substances. Pure substances have fixed or definite composition. So you can have a pure substance like water. You have just plain old H2O by itself. That is a pure substance. You could have something like sodium chloride, which is like a salt. And if you have that by itself, it's a pure substance. You could have an element that's by itself. So if you have just like copper by itself, that could be a pure substance as well. Now, we also can classify matter in terms of mixtures, and mixtures are where two or more different substances basically combine, but they do maintain their identity. And that's a really important aspect of mixtures, is those substances maintain their identity. And really what that means is, as we'll talk probably a little bit more in this chapter, what's happening here is this is more of a physical type change. And in a physical type change, as we'll talk, I think, a little bit later, a physical change really is one where we really don't change fundamentally what something is. It may perhaps look different, but you could still get back sort of the original substances. So, for example, if I did take my two pure substances here, if I took my water and my sodium chloride or my salt and I put it together, I will basically get salt water. And if you've seen salt water, it looks just like water, right? You really can't see much in there. It just looks like water. But the salt or the sodium chloride is actually in there. And when I put that together, that is a mixture. Although when you look at it, it may appear that, things have changed, things have reacted, but they really have not. And we'll talk about in this chapter, how you could get back both of those parts, the salt and the water can be reclaimed through processes like physical processes, like heating, cooling, and those type of processes as well. Same idea as well, if you took some sand by itself, that is a pure substance. You took also some water with that. That is also a pure substance. Again, if you mix those together, you have sand and water, which is a mixture. And different than the saltwater mixture, definitely if you took some water and you threw some sand in there, you would definitely see the sand right at the bottom probably. And obviously you would see the water part. So in this particular case, you can actually see both parts of the mixture, and they both do retain their identity. You could pour that through like a filter paper. You could get the sand back. You could retrieve the water as well. So when we talk about mixtures, and as we will, there's really two types of mixtures. There's one that are homogeneous mixture, which is what this would be. This is known as a homogeneous mixture. And much like the saltwater example, when we mix these substances together, they mix really well. It just looks like one thing, as opposed to over here with our sand and water. That is another type of mixture, which is known as heterogeneous. Mixture. And when we mix things like that, like the sand and water, although they are mixed together, you can mix them all day, they'll never like perfectly sort of mix together and look like one thing. And that's what's known as a heterogeneous type mixture. Any questions on that there? Here's sort of a flow chart of some of the stuff we're going to talk about. Matter can be pure substances. Pure substances can either be elements or compounds. Matter could also be mixtures, which will either be homogeneous or heterogeneous mixtures. And again, we'll talk about what all those things are as well. So I think what we'll do is probably a good place to stop, I think, before we get too far into everything. So we'll stop there today so we can talk about a couple of things. So as I mentioned, I think last week, we're going to have a quiz. And I believe I said we're going to do it on Monday, if I'm not mistaken. That's what I said. And that's let's see, that's 22nd, I want to say, 2/22. And it will be really, we're going to do it on chapter 2, I think. And again, chapter 1 didn't really have a lot of sort of chemistry in it and stuff like that. So the quiz will be on chapter 2. So what the plan will be is on Monday, we will lecture like normal at the start there, or whatever, 5:35. We will stop somewhere around probably, where will we stop? We'll probably stop somewhere around 6:30, I think. And you will then take the quiz at that point. And the quiz will be done, I think this time it'll be probably a Canvas quiz. And you will need to use Proctorial for this one. And you'll take it, and then afterwards, obviously, if you have lab, you'll go to lab. If you have discussion, you'll go to discussion at that point at 7. So that should hopefully give you enough time to do all that. Again, probably won't be super long, maybe 3-4 questions, probably problem-based type questions where you might have to show the work, submit the answer. I think the quiz will be a combination of, you'll have to enter it into Canvas, the answer, and there may be some problems where you'll need to upload the work. So it'll be kind of like the Proctorial practice quiz, where there was like the quiz, right? And then there was like the upload after it in the module. So it'll probably look something like that, just like that. There'll be like a little honesty agreement and all that good stuff. So honesty agreement, then I'll open up the quiz. You'll take the quiz, you'll have to answer it. And then immediately after you submit your quiz, you need to upload your work if there are questions like that. So that's sort of what it will sort of be like. Any questions on that? Also, a reminder that if you haven't done the Proctorial practice quiz, I think it's still up there and available for you to do it. It'll just be marked late. It doesn't really matter, but I highly recommend that you go do that before Monday. So there will